Welcome to Parasitology. Today, we are diving into the fascinating, albeit slightly unsettling world of Cimex lectularius, commonly known as the bedbug. Imagine settling into a cozy hotel bed, completely unaware of the tiny creatures waiting in the seams. We will explore their biology, how they feed, and the mathematics behind their explosive population growth. Let us get started. Now that we know what we are looking at, let us define exactly what this creature is. In the scientific community, the common bedbug is known as Cimex lectularius. It is classified as an obligate hematophagous ectoparasite. That is a complex term, but it simply means this is an insect that lives on the outside of its host and absolutely must drink blood to survive. They do not care about your food or the warmth of your home. Their only interest is a warm blood meal, which they typically seek out in the dark while you are fast asleep. Building on their classification, let us look at how their bodies are perfectly adapted for their parasitic lifestyle. Morphologically, bedbugs are dorsoventrally flattened. This means they look like they have been squished flat from top to bottom, which allows them to squeeze into incredibly tight cracks and crevices in your mattress. They are wingless, reddish-brown insects equipped with specialized piercing, sucking mouthparts. These mouthparts are designed to painlessly penetrate human skin, so the host rarely wakes up. Unlike ticks, they do not stay attached to you. Once they finish feeding, they quickly retreat to their dark hiding spots to digest and molt. To truly appreciate these adaptations, let us examine this detailed diagram of Cimex lectularius. Notice the overall oval, flattened shape of the reddish-brown body, which is key to their ability to hide. At the front, you can see the antenna and compound eyes used for sensing their environment and locating a host. Just behind the head is the pronotum, followed by the wing pads. Remember, they are wingless, so these are just vestigial structures. The largest portion is the segmented abdomen, which expands significantly when they take a blood meal. The scale bar shows they are only about 5 millimeters long, roughly the size of an apple seed. Having seen what they look like, you might wonder why we study such a small household pest so intensely. The primary reason is their massive psychological, physical, and economic impact worldwide. While bedbugs are not currently known to transmit infectious diseases, their bites cause severe allergic reactions, intense itching, and secondary skin infections from scratching. Beyond the physical bites, an infestation takes a heavy psychological toll, causing extreme anxiety, insomnia, and social stigma. Economically, the hospitality and travel industries lose millions of dollars every single year due to extermination costs, ruined furniture, and severely damaged reputations. Understanding their impact naturally leads us to ask, why are they such a nightmare to control? The answer lies in their population dynamics. A single pregnant female introduced into a home can trigger an entire infestation because she lays several eggs every single day. Inside a climate-controlled bedroom with sleeping humans, they have an abundant food source and a perfectly safe environment. Under these optimal conditions, their population does not just grow steadily, it grows exponentially. This explosive growth is exactly why early detection is critical and why exterminators rely on mathematical models to predict the severity of an infestation. To predict this explosive growth, we use the standard exponential population growth formula. Conceptually, this formula describes how a population multiplies continuously over time when resources are unlimited. Let us break down the symbols. N of T represents the total population of bedbugs at a specific time. N0 stands for the initial number of bedbugs that started the infestation. The letter E is the mathematical constant, approximately 2.718, which naturally describes continuous growth. The variable R is the intrinsic rate of increase, depending on egg laying and survival rates. Finally, T is the time elapsed. If the room temperature increases, the growth rate R goes up, causing the total population to skyrocket much faster. Before we move on, let us see this formula in action with a concrete example. Suppose a traveler accidentally brings home 2 bedbugs. We are given an initial population of 2, a continuous growth rate of 0.1 per week, and a time period of 12 weeks. We want to find the final population. We substitute these values into our exponential equation. The exponent becomes 0.1 times 12, which is 1.2. Evaluating e to the power of 1.2 gives us a growth factor of approximately 3.32. Multiplying this by our initial 2 bugs gives us 6.64. So the final answer is approximately 7 bedbugs. Note that in reality, the biological growth rate is often much higher, which would lead to hundreds of bugs. Now that we have modeled how their numbers multiply, let us explore another fascinating mathematical aspect of bedbug biology: the sheer volume of blood they consume. A single adult Cimex lectularius can drink up to 6 microliters of blood in just one feeding. While that sounds tiny, when an infestation grows exponentially into the thousands, the cumulative blood loss for the human host becomes highly significant. In fact, chronic feeding by a massive infestation can actually lead to anemia, particularly in children or the elderly. To understand this physical toll, we need to calculate the total volume of blood extracted by a population. This brings us to a straightforward linear model to calculate blood loss. Conceptually, if we know how much one bug eats, we just multiply it by the number of bugs feeding. In this formula, V total represents the total volume of blood consumed by the entire bedbug population. The variable P stands for the total population, or the number of feeding bedbugs. The variable V single is the volume of blood consumed by one individual bedbug, which we know is up to 6 microliters. Because this is a direct multiplication, the total volume scales linearly with the population size. If the population doubles, the amount of blood lost by the host also doubles. Let us apply this formula to a severe infestation scenario. We are given a population of 5,000 adult bedbugs, and we know each consumes 6 microliters of blood. We want to find the total blood lost by the host in milliliters. First, we multiply the 5,000 bugs by 6 microliters, giving us a total volume of 30,000 microliters. Since microliters are hard to visualize, we convert this to milliliters by dividing by 1,000. The final answer is 30 milliliters of blood. Physically, this is roughly equivalent to losing 2 tablespoons of blood in a single night. This mathematical reality perfectly highlights the severe physical toll these parasites take on a human host. We have covered a lot of ground today, so let us review the key takeaways. First, Cimex lectularius is a highly adapted, dorsoventrally flattened ectoparasite that relies entirely on human blood to survive. Second, while they do not transmit infectious diseases, their presence causes severe physical itching, psychological distress, and significant economic damage. Finally, because they reproduce exponentially in optimal conditions, A small problem can quickly become a massive infestation, causing measurable blood loss. Understanding their biology and the mathematics of their growth proves that early detection and disrupting their life cycle are the absolute best ways to protect ourselves. Great job following along with the math and biology today.